Okay, it seems to have sort of flatlined for people joining, so we'll go ahead and get started. Thanks everybody for coming to the International EPR Society virtual seminars. We have just sent out our winter/spring schedule. We didn't really take a break like we usually do in between the fall schedule and the spring schedule because we had quite a long list of speakers. So we thought, oh, we'll skip the break and just keep on rolling. Yeah, but on the email, you'll see, those of you that receive our emails should see that we have extended the calendar through what I believe is June now. And today's speaker is Kaltum Abdiaziz. She comes to us currently from her postdoc at the Max Planck Institute for Chemical Energy Conversion, where she is studying spectroelectrochemical techniques using some rather creative EPR spectroscopy that she'll talk about today. And these are to study redox reactions, and she's particularly interested in iron cyano oxygen reduction catalysts. She got her master's in pharmaceutical chemistry from the University of, and I hope I say this right, Leicester?
No, Leicester.
Leicester, you said Leicester,
yeah.
okay.
Yeah.
She did her PhD with Maxi Rossler in the topic of also spectroelectrochemical techniques, studying redox-based reactions. And then she did a short interim postdoc before coming to Max Planck at Queen Mary with Guy Hankey on the topic of TROL effects in ferredoxin NADP plus reductase activities. So with that, the floor is yours, Kaltum. I'm excited to hear you talk today. Take it away.
Thank you for the invitation. And I have to say, Takuma apologizes for not being able to make it. And I will therefore then just take over and talk about his part, or his contributions also in spectroelectrochemical EPR. So yeah, my topic, like Joseph said, is an introduction to spectroelectrochemical EPR. I thought I would go through like a brief introduction into electrochemistry, and then the benefits of spectroelectrochemical EPR and why I think it's necessary to have this technique. And then I will talk about several different types of spectroelectrochemical setups that I've developed or been involved in developing. And then finally, where I think the future of spectroelectrochemical EPR is. So electrochemistry is the branch of chemistry which concerns with the relationship between electricity, so that's the flow of electrons, and a chemical reaction, so redox. And typically this happens at the interface between an electrode, so a metallic conductor, and an ionic conductor, so the electrolytes. And there are two types of electrochemical setups, which the first of which is a galvanic setup. And in this setup here, you convert chemical energy into electrical energy spontaneously. And an example of this is alkaline batteries, where you have one half of your cell in one beaker or one side of your setup, and then the other half in another setup. And this is, therefore, then you have a bridge between them that connects the two. And then there's the electrolytic cell, where you have your electrodes in a cell, where you look at the electrical energy to drive, you use electrical energy to drive chemical reactions. And these are usually used in electroanalytic measurements. This setup here can be have two different configurations. Essentially, you have the first, which is a 2-electrode cell, and this is a simple setup where you have 2 electrodes immersed in an electrolyte and connected to a potentiostat, so a power source. And then you have a 3-electrode cell where you have a 3rd electrode present, which is called a reference electrode. And all of these are now then connected to your potentiostat, similar to your 2-electrode cell. And in the 2-electrode cell, you usually do experiments like electroplating, where having a precise potential control is not essential. Whereas if you want to have a a real control over your potential or your flow of electrons, then you would need a 3-electrode setup. So there are several components, and in my research, I usually use a electrolytic cell, and in particular, a 3-electrode setup. And there are several components in your electrolytic cell, the first of which is your working electrode. And in your 2-electrode setup, this is either an anode or a cathode, depending on the reaction that you're investigating. However, in a 3-electrode, we call this the working electrode, and it's where the reaction of interest takes place. And its potential is precisely controlled and measured by the potentiostat. And so in a 3-electrode cell, you have, there are several types of materials that are used quite heavily as your working electrode. So inert metals such as gold and platinum are quite used. By far, the most commonly used material is carbon, whether that's glassy carbon, boron doped diamond, or pyrolytic graphite edge. And then there are also semiconductors that you can use, such as indium tin oxide and silicon. The second component in your cell is the counter electrode. And in the counter electrode, it serves as a balance to balance the charge that you have of the to balance the charge in your electrochemical reaction. So in the 2-electrode setup, this would be, I guess, if you had your oxidation happening on your working electrode, then this would be your reduction, or vice versa. And in this 3-electrode, then essentially you want this to be completely inert and not influencing your reaction. And so as such, inert materials such as gold, platinum, and carbon are used. Another component of your cell is the electrolyte, and this is responsible for carrying a charge between the electrodes. And so you want this to have as minimum resistance as possible. And so there are several different types. You can either use ionic species, such as, I guess, protons or sodium or ions, I guess. And then fused salts, such as sodium chloride or potassium chloride, or you can use ionically conductive materials as like naphthalene to act as your electrolyte. But it's worth it to remember that the electrolytes should have a high ionic conductivity and stability under the reaction conditions. And then finally, the reference electrode, which is present only in a 3-electrode setup. And this is responsible for measuring and controlling the working electrode's potential without having itself pass any current. So it's in the name, it's the reference point to your working electrode. And so there are several. So you have the standard hydrogen electrode, which is the conventional reference electrode that everything is referred to. However, it's not always the easiest reference electrode to use. So there are silver chloride, saturated calomel electrode, and then also silver nitrate or silver chloride, depending if you're using aqueous or an organic medium. There are two ways you can do your electrochemistry. So the first of which is a solution electrochemistry, where your species of interest is dissolved in your electrolyte. And what happens here is then your species diffuses to the working electrode, either gets oxidized or reduced, depending on the potential that you're applying, and then goes back into your bulk solution. The other way you can do it is surface-bound electrochemistry. And so where you have your species of interest directly immobilized onto the working electrode. And then as a result, you get a direct electron transfer between your working electrode and your molecule of interest. So in this scenario here, you are diffusion limited. So if you're working with complexes or molecules that have very poor diffusion, then it becomes quite sluggish and problematic. Whereas here you're not diffusion limited, but anchoring these molecules or these complexes onto the working electrode is not always the easiest thing to do. And you could get a complex surface chemistry going on. So here I show you just a schematic diagram of all the different processes that can happen on the electrode. So this is an example of a solution electrochemistry where you have your species of interest, so either oxidized and reduced by the electrode. You could have adsorption and desorption going on at this in your system. Chemical reactions could occur of your species once it's further away from your electrode, and then also mass transfer. So what's going on here, it's closer to the electrode, we can refer to it as a fast regime, and then further away in the bulk solution as a slow regime. So in general, the current that you experience in your system is affected by all these different processes. So your mass transfer, the electron transfer to and back from your electrode, any chemical reactions that are occurring, and in a steady state condition, all of these are kept the same, but you might get some sluggishness from one process or the other, and this results in the what we call the rate determining step. So with electrochemistry, you can really investigate all of these parameters, processes that's going on. So the first type of experiment that we do in electrochemistry quite heavily is voltammetry, where you are scanning between two potential limits in a linear fashion. So I hope this works, but this is like a little animation of how it works. So you have your reduced species, and then once you get to a certain potential, it gets oxidized, and then electrons move from your reduced species to your electrode, and then you scan again in the reverse, where the opposite happens, where electrons go from your electrode to your species, and then it gets reduced again. And some of the information that you can get from voltammetry includes reduction potential. So this peak here is the oxidation peak, and this one's the reduction peak. And in between these, what the potential is between these two peaks is the reduction potentials. You can investigate any diffusion coefficient, diffusion going on in your system by looking at the dependence of your scan rate, which basically is how fast you scan between your two limits. And then also you get information about your redox reaction, whether it's electrochemically or chemically reversible. So the other technique that I use quite often in spectroelectrochemical EPR is chronoamperometry or chronopotentiometry. So the first is that where the potential of the working electrode is kept constant by varying the current over time. And the opposite for chronopotentiometry, where the current is kept constant and the potential is varied. And again, a lot of information can be determined from chronoamperometry, which includes the kinetics of your chemical reactions, against similar to voltammetry, diffusion processes, adsorption, desorption processes. You can use chronoamperometry for electrolysis and electrodeposition of materials on or complexes onto your working electrode. The equilibration time constant of electrochemical setup, which is how fast the cell equilibrates once you apply a potential or a current. And then stability tests for electrochemical systems. There is one parameter that is quite important in electrochemistry, which is the ohmic drop. And this refers to the voltage that's lost due to the resistance in your electrolyte or somewhere in your system. And so you have several things that can cause an ohmic drop, which includes solution resistance. So if your solution is not sufficiently conductive, you get resistance from your solution, and so you can that adds to your ohmic drop. You can have uncompensated and compensated, which comes from distances between these electrodes. All of these add to your ohmic drop, which means that the potential that you're applying from the potentiostat is not necessarily the same as the potential that's experienced in the electrode. And so some of these resistances can be compensated by potentiostat, and here I show you an example where, so the black trace here is a system where there is no resistance, and the blue here is where you have some resistance, and the orange is the potentiostat compensated. And so you can see that it does compensate for a significant amount of the resistance. However, there are still some that it's not compensated. So to try to minimize this is very important. So spectroelectrochemistry is, like it says in the name, the combination of electrochemistry with a spectroscopic technique. And I hope I showed you with electrochemistry, you can determine a lot of information regarding the redox reaction. And with, however, one drawback from electrochemistry is you get no structural information. And that's why it's combined with a spectroscopic technique where you can get detailed structural information to get more out of this, more out of the technique that you're using. And the spectroscopic technique that I'm combining electrochemistry with is EPR. I'm sure I don't have to convince you or the audience how useful EPR is, but since redox reactions involve electrons moving or being transferred, EPR is in my opinion, one of the useful techniques that you can use to study systems. And so with the combined setup, we're able to monitor spectroscopically in situ and operando redox processes and really capture any intermediates that you are forming during a reaction. So a lot of mechanistic information can be obtained from spectroelectrochemical EPR. So there are two ways that I will talk about how we perform spectroelectrochemical EPR. The first is the conventional way, where the electrochemical setup is miniaturized into an EPR tube. And the second is where the EPR spectrometer is miniaturized instead of the spectroelectrochemical EPR. But before I do that, I thought I would discuss a little bit what an ideal spectroelectrochemical EPR setup is. And in my opinion, it's important that you have a working electrode which has a high sensitivity and ideally not give you any interferences, so no background signals from your electrode, which sounds easy, but not always the easiest thing to do. You would like to have a wide potential window and solvent accessibility because the electrode material, the electrolyte, and the solvent all change the potential window that you have accessible to you. So in an ideal setup, you want to maximize this potential window so that you can study a wide range of systems. And so either it would be nice to have all of this in one setup, which is not realistic in my opinion, or to have a system where you can easily interchange or exchange these different components so that you have a wide range of potential window. You want to be able to study a large range of molecules and complexes, so irrespective of their size. So proteins, for example, would be very nice to be able to study, or to very small molecules like nitroxide. It would be great to really get as much information from EPR as possible. So to have a spectroelectrochemical setup that you can study with multi-frequency, CW, and pulse. And then finally, an electrochemical setup where you can study both in steady state conditions and then also in catalytic without any limitation. So no ohmic drops and no limitation in terms of substrate diffusion. So we know, I hope I showed you that these two techniques are a great pair together to get as much information as you can from your redox reaction. However, the problem comes from their conflicting requirements. So EPR, you want to minimize or at least avoid any conductivity in your system. So lossy samples and conductive solvents are a problem because this interferes with your microwaves. And so electrode material, since you are generating your species of interest at the electrode, can influence or affect your ability to measure EPR. Whereas in electrochemistry, the conductivity is a requirement. So you need to minimize any resistance coming from a lack of conductivity. And so lossy and conductive solvents, so electrolytes or aqueous solutions, are a necessity. And then in the sample volume that you have in electrochemistry, it's typically in the milliliters range, whereas in EPR, it's the microliter range. So that's another conflicting requirements that you have. And it becomes more apparent when you go to higher frequencies. So EPR at X-band, you have a 4 millimeter space in your EPR tube, and this gets significantly smaller the higher frequency you go. So you can imagine making a spectroelectrochemical setup at higher frequencies is very difficult. And so you will see that most spectroelectrochemical setups are designed for X-band EPR. There are one or two, at least in my opinion, my knowledge, that they are in Q-band, and none that I've come across for W-band, at least in situ. Maybe there are some ex situ approaches, but not in situ. So the first setup I developed here at the Max Planck is for a commercial X-band spectrometer. So we have a quartz tube with either 4 millimeter or 5 millimeter diameter. And then at the top here, you have the top part is just the electronic connections. And then you have an inlet and an outlet with a piece of tubing that goes all the way down to your sample, where you can introduce different gases. And so for the working electrode, I use a gold wire, which I flatten to increase the surface area. And then my reference is a silver wire, which is a pseudo reference because I am not able to use a real reference due to space constraints, and then a platinum tube as my counter. And so in this system, I typically work between this range, so 5 to liquid nitrogen temperatures. And so the way I do these experiments is I drop cast my catalyst or whatever it is that I'm working on onto the electrode, and then I assemble my setup and measure the electrochemistry inside the spectroelectrochemical setup. And then I compare this usually with the exact same system, but in a standard electrochemical setup to make sure that there is no differences between the two. I then apply a potential, usually for about 20 minutes, but this can be reduced. And then I flash freeze this in liquid nitrogen, and I wait for the current to go back to 0, to indicate that everything is frozen. And then I take my sample to the EPR spectrometer and I measure. And so this is, I guess, not a real in situ setup, but a quasi in situ, where I'm all in one tube. However, I freeze and then I do the measurements. And so in this system, this setup, I applied it to these, they're called FENC catalysts, which is characterized by an ion with 4 nitrogens in a carbon framework. This is the assumed structure for the catalyst, but the nature of these, the active site, is quite unclear. And so this catalyst is of interest to us because it's an oxygen reduction reaction, and it works similarly to the platinum that's used now commercially. However, the stability is a real issue. And so what we did was to try to use in situ EPR to get more information about the active site. I forgot to mention, but one thing about this catalyst is to get a very active catalyst, we have to pyrolyze the material, all the different precursors at a very high temperature. So it's not a very clean catalyst. So try to disentangle all these different ion species is very difficult, and this is the main aim of our application. And so that's what we did. I measured the CV at room temperature, and then I applied the potential at room temperature, and then I go to EPR spectrometer and I measure the EPR. And so the one thing we did notice is that this signal is starting to disappear as you go from higher potentials to lower potentials. So it's electrochemically active. I won't go into too much detail since my talk is about the setup rather than the results of the application, but I hope that I showed you that with this setup, we have potential control over our system. So the second system that I will talk about is a setup that I developed in my PhD in Max Zero-Wesler's group, which is a proton film electrochemical EPR, where we immobilize small molecules and proteins onto these homemade electrodes. So these mesoporous ITO, where you can see from SEM that it has a mesoporous structure. And the reason we went for this material is because it's highly tunable and you have a very high surface area. And again, similar to my previous system, the temperature range is 5 to 77 Kelvin. And the reason why we have to work at this temperature is because there's a lot of volume of electrolyte, which at room temperature is not the easiest thing to do. It is doable, but it comes at a cost of distortions in your EPR spectrometer, measurement, sorry. So the one system that we worked on is these nitroxide molecules that were immobilized covalently onto the electrode. And so here the CV, if you look at it, you can see two redox peaks. And if you apply the potential and measure the corresponding EPR, we see that the signal is disappearing. And if you plot that against a Nernst curve, we see that this the midpoint potential that we obtained from from the Nernst curve matches very well with our CV. So with this, we are fairly certain that we have a direct and accurate potential control. So the third setup that I have developed is for the Magnetec, so the benchtop spectrometer. And so in order to get a setup that works at room temperature, I had to significantly reduce the volume of my EPR tube. And so here I have a small tube, which is about 2 millimeter diameter at the bottom, connected to a much larger one, which is a 6 millimeter outer diameter. And my working electrode, which is the gold wire that goes all the way down to the bottom. And then I have my platinum tube as my counter, and then a silver wire as my reference electrode. So in this setup, I'm able to adapt it to flow. So all I do is have a connection here at the bottom, which is then connected to a potential per-started pump. And then with this setup, we are able to work at liquid nitrogen temperatures, but in our spectrometer, benchtop spectrometer, we can only go down to 93 Kelvin, but also high to about 520, which is about 250 degrees. So I have tested my setup from 93 all the way to 100 degrees, but I have not gone higher, but the specification for the Magnetec allows you to do so. But yeah. So to test my system, I worked with a small molecule called methyl-vialogen, which is shown here. When you dissolve it in solution, you get this dication system. And so it undergoes two 1 electron reductions, so to this methyl radical, and then one more to the neutral compound. And so with this, I then placed it inside my inside the Magnatech, where the conditions I had for the electrochemistry is a 1 millimolar concentration of this complex in 0.4 millimolar KCl. And these are usually the standard conditions for an electrochemical setup. And so what I did was then I applied several different potentials and then measured their corresponding EPR. And if you look here, the CVs, I compare it between a standard electrochemical setup, which is red, and then my setup here, which is black, and they agree very well together. So again, I'm sure that in my setup, it's working like an electrochemical setup should work. But that was a test subject to see that everything was working. But to go further, we worked with our collaborators here at the MPI Keck, so Durian and Nicholas Kafer, where they were looking at the conversion of CO2 into these C2 products. The mechanism of this was unknown to them, but they speculated that it undergoes through a radical. And so we thought we can use the spectroelectrochemical setup to study this. And that's what we did, where we applied a potential. So here I applied a 2.3, so where the reduction is happening. And then I see an EPR signal, which with 7 lines, and that follows very nicely to a Pascal triangle. So with this, we were able to identify the radical, the radical intermediate in this reaction, and we saw that we were having 2 different isomers. So we saw the Z isomer and the E isomer in 50-50% contribution. And then we went on to a variation of the complex. So that was 2 methyl groups. And so here we then worked with 2 phenyl groups. And similarly, we did the exact same experiments, and we saw that we have 2 different species. However, one in majority and at 95%, and then the other one at 6%. And we think it's this E isomer due to the steric hindrance. And then the final setup, which was developed by Takuma, which is what I explained earlier. What I was doing was an electrochemical cell in the spectrometer, whereas he is doing a spectrometer in an electrochemical setup. And the main reason for this is the conventional way of doing it. You have a geometric restriction, and lossy samples are really not the easiest things to handle. Whereas in spectroelectrochemistry, this EPROC, so here you can see an image of the actual sensor, so the chip. You can just place this inside an electrochemical setup, and this coating that it has prevents it from degrading, one, and then also any interference that's coming from lossy samples. So it's non-resonator based. It's quite, once prepared, it's quite flexible and simple to use, and it's standard. So here is the setup that he used, where, so at the back here, you can see the PC board with the setup. So the EPROC sensor, and then a platinum coil for the counter electrode, a real silver chloride reference electrode here, and then he uses this gold, flattened gold sheet as the counter. So here he's using real or like standard electrochemical electrodes. And then all of this is placed inside your magnet, so your electromagnet, and you can do the measurements. So again, methyl was used as a test subject, where he scanned, and you can see that the electrode starts to change color when you go towards, I apologize for that. That should not be there, but it changes color. And then the color starts to disappear as you're going towards the second reduction potential. And in the reverse, you should also see that the color intensity goes higher when you go towards the reduction potential of your methyl halogen radical, and then back to an EPR silent dication. Yeah. So again, similarly to what I've showed you before, he applied a series of different potentials and then measured their EPR intensity. And again, similar to my previous examples, the potentials that you get from plotting the intensity against the potential from EPR matches very nicely with what we determine in the electrochemistry. So saying that we have a direct and an accurate potential control over our system. So the sensitivity was able to go down to in the in situ SEC-EPROC is about 250 micrometers, but there are further improvements that are currently ongoing to lower this sensitivity. But he can also do a simultaneous in situ spectroelectrochemical EPR, where instead of applying a potential and measuring, he just scans the cyclophotomegram and then measures at the same time. So both electrochemistry and EPR are happening at the same time. And so with this, you can monitor any changes that are occurring as a function of potential. Yeah. And the final type of experiment that he'd done in his system was a transient electrochemical experiment where he sits at a maximum intensity and then applies a potential. So in this case, he applied here at where this blue arrow, and then measured the intensity of this signal as a result of the potential that's applied. So with this, you can really see the increase in intensity, the leveling out, and then also the decrease of the intensity. So if you want to look at systems where species are being generated very fast or in very low concentrations, this transient spectral electrochemical EPR would be very nice. So and at this point, he went down to 1 second per point. However, with rapid scan, he can go down to milliseconds. So to kind of summarize all the setups that I've shown you and some with the literature, here are just some characteristics that I've thought that are important for the setup. And you can see that at least for the CVs, that all setups work very nicely, but there are some distortions in some setups over the other, depending on how easy it is to put your sample inside the spectroelectrochemicals, the EPR spectrometer. Sensitivity is also another issue for some setups and not for others, but yeah. So to where I think the future of spectroelectrochemical EPR is, I've put it down to three different things. The sensitivity needs to be improved, spectral resolution, and species identification, and also operando. And in sensitivity, I think if in order to see fleeting intermediates in a reaction, we need to have a very good sensitivity. So in my opinion, some of the improvements that can be done are rapid scan, even high surface area electrodes, but also electrochemical modulation. In terms of spectral resolution, this is an issue when you're dealing with heterogeneous catalysts, for example, where I showed you in the FENCs, where you have a number of different paramagnetic centers, and you're trying to see which one is the catalytically relevant species. And so for this, maybe as a topic labeling or multi-frequency spectroelectrochemical EPR could be handful, but also pulse. And then finally, operando, where the biggest challenge, in my opinion, is the operando system for paramagnetic centers that require cryogenic temperatures. And so these systems right now, I think, don't really exist. And this is where I think most development could go into. But also electric catalysts that require harsh conditions like gas evolution or very high or low potentials. Currently, I don't think this is accessible to spectroelectrochemical EPR. And with that, thank you for your attention, and also thank you for my group. And Takuma says thanks.
Well, that was a very nice presentation. Thank you. We will now open the floor for questions. And so if you have questions, feel free to just raise your hand, unmute your microphone as you wish.
Hello.
Friedrich, go ahead.
Thank you a lot for the nice presentation. I have multiple questions. First, starting with the silver chloride pseudo electrode, how do you coat it with silver chloride?
So normally I in a chloride containing solution, I electrodeposit it on.
Okay, and how thick does this layer have to be? Do you know any? Do you
No,
make
so I
any
have
tests or just wait till it's turning black?
essentially yes. Wait for it to turn black. But I have not studied this in a lot of detail actually. But my experience is even without the coating, it still works fairly well. You just need to, at the beginning of your experiment and then also at the end of your experiment, do a comparison with a real reference electrode so that you know what your offset is.
Okay,
And
because
yeah.
So yeah, because I'm having a lot of problems with a lot of drift in my setups. Even so that the peak separation goes below 57 millivolts, because on the oxidation part you get your peak, and on the way backwards the signal is already drifting, so that the peak separation gets even smaller than 57 millivolts. And also on doing multiple scans, I have drifts of, I don't know, 1 volts maximum, so quite a lot.
Okay.
But you have nothing, you have not experienced something like this?
No, I have not experienced something like this. Can I ask what conditions, like the electrolyte conditions that you're using in the system?
In DMF acetonitrile,
Okay.
but I'm also having a very, very small cell, so it's 2 millimeter inner diameter, or 1.5 millimeter inner diameter.
Right.
Yeah, so maybe it's something due to the limited geometry.
I really think so. And actually in my setup here, where I have a small tube, if the tube is from like 2 millimeters from the bottom all the way to the top, my electrochemistry is very bad. I need this large, I guess, reservoir or larger part in order for the electrochemistry to work. I have currently, I'm looking at if there is a way to model the potential up here versus down here, if there are any differences. But from the EPR response, it seems like there is not any differences. The potential that I get from EPR matches very well with
How
my
long
CV.
is the smaller part?
So this is about 5 millimeter length.
Okay, yeah, I have seen some potential difference. It's not a lot, especially if you're like, it will get important if it's longer than 1.5 centimeters or something. But there would be my next question. Do you have seen any influence of the distance between the counter electrode and the working electrode play a role?
This is the most important thing in my opinion. And maybe I can show you, I have an extra slide. 1 second, sorry. Second. So in my experience, the distances between your electrode is the one that influences most what your CV looks like. So here, for example, where I played around with different positions and I compared it with my standard electrochemical setup. So here where I have it all at the top and I have much larger volume, they match quite well. But when I have the counter further away, the CV already starts to distort. And again, if the reference is further away, it distorts again, right?
Yeah.
But in this configuration here, where I have the reference electrode at the very top and then the counter all the way at the bottom, I have, again, it gets better again. So sorry.
Are all the electrodes that you show in the picture, are they all de-isolated? Or is there some isolation to a specific point?
So the counter is completely bare to kind of maximize the area of the counter. The gold is coated to a certain point. So in this example here, it's coated all the way, I guess, to that position here.
Okay, I see.
So that they are not coated. And the reference is coated, mostly entirely coated. However, the bottom 1 or 2 millimeter is exposed.
Okay, I see.
Yeah.
Okay.
So yeah, you kind of need to keep them away from each other.
Yeah. And also the last question. So in my setup, I'm having a lot of trouble going to higher potentials. So for example, if I want to apply 2 volts at the working electrode, my counter electrode experiences up to 3 volts or more, which will then at that point decompose the solvent at the counter electrode, and then you run into a lot of troubles with bubbles forming and so on. Have you experienced something like this as well?
I think this is a current issue for spectroelectrochemical.
Okay.
Outside of this window, I would say minus 1.5 to 1.5, it becomes very tricky. And in my application, I have not moved to the other side, but this is where I think Takuma's setup is more ideal, where it's just an electrochemical setup. So as long as from a electrochemistry point of view, you could reach these points, it should work.
Yeah. Okay, yeah, because I want to measure my compounds at 2.5 volts and plus, so I'm having trouble with getting a cell to work.
Again, maybe the electrode materials is crucial at this point. What counter working that you're using, but yeah, you will definitely run into problems at these extremes, in my opinion, for sure.
Okay, but thank you a lot.
No problem.
I learned quite a lot. This will help me. Thank you.
Okay.
Other questions? Sebastian, please go ahead.
Yeah, thank you. Thank you for your talk. For the on-chip EPR setup that you show here, I think you showed some spectra with resonances around 14 gigahertz or so. Do you know what the frequency range of the EPR on-chip is and what limits it?
No, sorry. My knowledge of this setup is very limited. I think Takuma is the person to ask. But yeah, sorry, I can't answer that question.
Yeah, no worries. Thank you.
I will ask him for you, I guess.
Okay, thanks so much.
Yeah, no problem.
I think actually Michaela's in the audience and could probably answer that if he's paying attention to his microphone.
Maybe someone else can answer for you.
The bandwidth, can you hear me?
Yes, thanks.
Yes. Sorry to call you out, Michaela.
So the bandwidth of this chip is about 2 gigahertz. And yeah, you can, the oscillating frequency can go from 13 gigahertz to 14 gigahertz and half, something like that.
Okay. Thank you.
Yuji, go ahead.
it's a very nice talk. Thank you. I have a very naive question about the spectrum showing here. Is it a CW-EPR
Yeah.
experiment?
Mhm.
And why are we seeing this line shape?
So this is measured in the frequency domain, if I'm correct. I mean, Michele, you can correct me at any point. So here, instead of varying the magnetic field like you do in conventional EPR, you're scanning the frequency.
Right, okay, so it's a different detection scheme.
Yeah.
Okay, great, thank you.
Yeah.
And also, have you seen any broadening effect due to any of the electrostatic or interactions?
Surprisingly, no. There are some strange things which I cannot explain currently going on with these, like placing a metal inside an EPR spectrometer. For example, the quality factor doesn't change as much, and when I try to do pulse EPR, I can decouple much better actually with a metal piece inside.
Okay.
So there are certain things that I cannot explain, but all for the good so far. Like they've been in my favor, which is good.
Okay, that sounds great.
Yeah.
Thank you.
Other questions from the audience? While people are thinking about their questions, Veronica sent in the chat that there are the methylviologen is actually quite toxic, and she has sent a link to some non-toxic substitutes, but they're not commercially available. I'm not a synthetic chemist, but the conversion doesn't look too famous last words intensive. Veronica, you want to comment on that by chance? I see your hand up.
Yeah, I don't know if I'll be able to unmute, but
we hear you fine. Yeah.
So or my camera, I don't know if my camera will work. So we used to use methylviologen all the time in photosynthesis research, and we moved away from it. We use ferro and ferricyanide instead. And you can see a color change if you do that electrochemically, and has a nice, electrochemical signature, CV. But it doesn't have a great EPR spectrum at room temperature, obviously, right? Because it's metal.
Yeah.
Right. So the other thing, so just so that people know when you're handling it, to be careful and use as minimal amounts as you can, because it is actually really toxic. The other thing I would say that I was going to ask you is, you mentioned drop casting. So back in the day, 2015, when Adam Kinney was working for me, we started doing electrochemical EPR on some of the Dan Nocera catalysts. So we were electrodepositing cobalt phosphate catalysts onto the electrodes. And we did essentially what you did, which is to put them at a potential and then trap them and freeze them and go do the EPR spectroscopy. Have you been able to electrodeposit catalysts so that you can tell at what point in the electrodeposition you make an active, water oxidation catalyst? You mentioned drop casting them, but I haven't seen anybody do what we did. We never published it, but I'm wondering why that's so hard. I mean, it was hard for us, but I'm hoping other people have been able to do it.
My experience, no, I've not electrodeposited anything. I'm currently working with another collaborator here at MPI Keck, where they do electrodeposit their catalyst onto the electrode. We've run into issues with the gold electrode. It seems as though it's on there, and then once we apply a certain potential, it just all falls off. So now we are exploring other materials. I've avoided carbon-based materials for spectroelectrochemical EPR because they can give you, or they generally do give you, a background signal. So you get this radical coming from your electrode, which is changes with the applied potential, but it seems as though maybe that's I should go back to that, at least in this application that I'm currently doing with electrodeposited catalyst.
So we use two kinds of catalyst. We tried using ITO and then electrodeposit. The other one that we had success with is using quartz and then putting a chrome or titanium chrome or some other interface layer between the quartz and the platinum, and then using the platinum to do the electrodeposition. And so that did not, when we froze and thawed it, that did not crack the electrode. And the skin depth was thin enough that we could still do the EPR spectroscopy without losing a lot of, killing the quality factor. So that's how we did it. And then we soldered on, we basically glued on, leads and everything to that electrode. So, but I'm happy to send you anything, since we didn't publish it, I'm happy to send you whatever we have to help you, do whatever you want to do with it.
Yeah, that would be awesome.
Yeah, just contact me afterwards and I can send you whatever.
Sounds good.
Yeah.
Sounds good.
Any other questions from the audience before we close the session? Okay, if there are no further questions, let's thank our speaker one more time. Kaltum, that was a great presentation. And look out for our emails to announce the next presentation in 2 weeks. I hope to see you all again there. Thanks so much for attending, and enjoy the rest of your day, evening, morning, wherever you might be in the world. Thanks, everybody.
Bye.